We have talked about intrinsic semiconductor material, which has electrons and has holes and has equal numbers that are created as temperature rises or as something happens. But intrinsic material is not particularly good for much of anything, mostly because the charge carriers are balanced and we need to do something to either make more electrons or more holes. So we have to tip the balance one way or the other with the charge carriers to actually make semiconductor devices work. So I'm going to talk about just briefly about how impurities are added, and then next week we'll talk, Thursday. This is only Tuesday, isn't it? Yeah, Monday and Tuesday to me feel like an entire week. So by the time I get here, I feel like it must be Thursday by now, but it's evidently not. So Thursday, we will talk about extrinsic material, which is material that has been doped, but we will talk about the doping process today. So when semiconductor material is doped, or some kind of impurity is added, you can make the conductivity or resistivity, they're just inverses of each other, vary over a large number of orders of magnitude. So they can be really, really different depending on how the materials and how the impurities are added. There are two general methods of which I'm going to tell you kind of very briefly and in general how they're done. So the two basic ways of doping. One is diffusion, which came about in 1952. The other is ion implantation in 1958. And the two guys who came up with this all kind of worked together. Pretty much all of this stuff was done at Bell Labs, so it's not like two people at two different countries or anything. They were all working together and they just came up with different ways of doping. So we're going to talk about diffusion, since all my words are going away now. And diffusion, which you learn about in chemistry, is just when you have atoms in a real high concentration moving and distributing themselves over some kind of area that has a lower concentration. And diffusion actually is one of the ways we make current in semiconductors, but that is still a couple weeks away before we actually have current. It's a little while yet. But basically, atoms move from some area where there's a high concentration of impurities towards a lower concentration. And what happens is wafers, just intrinsic silicon wafers, basically are exposed to these dopants, and then they move through the solid crystal lattice in whatever way they do. There's a couple different ways they move into the lattice. One is something we call empty space diffusion, and that's basically the impurity atoms find empty spaces and stay there. We can have interlattice diffusion, and that's basically the atoms are kind of moving in the lattice, but they aren't part of the lattice. And then there can actually be kind of changing of places where some impurity atoms are changed with intrinsic atoms. And all of this stuff happens when diffusion happens. So all of this, and it sounds messy, and it is kind of messy, because dopants are going in there, but they're not all going to do the same thing, and they're not all going to end up in the same place, but they are going to kind of work their way into the material. And basically, you can either do diffusion with a limited amount of dopant, so put some on the top and just kind of let it sink in, or you can have an unlimited amount where you just keep putting it on and putting it on, putting it on, putting it on. Limited means that once you put some in, it goes down into it, but eventually the concentration that you have on the surface kind of decreases, obviously, because you're not what do you call, what is that word? I have no idea what that word is. Reapplying, that's a great word. I like that word. Yes, you're not reapplying more dopant. Unlimited means that basically there's going to be a strong concentration at the surface, and as stuff diffuses in, more of it comes in on top, and that's basically two different ways that you can get dopants to come in. Now, so there's kind of a couple different ways of exposing the wafer to this kind of dopant, whatever they may be. But there's also different forms they can be in. So we can use, say, a gas source. So there can actually be gaseous dopants. And basically the wafer is just stuck into a place that has all this gas, that has all these impurities in it. And then it just works its way in. So once it's exposed to any of this stuff, it just works its way in by diffusion. So once it gets to a certain point, that kind of all takes place. You can take slices and put them between solids and kind of make a semiconductor dopant sandwich. And again, the dopants will work their way into the wafers. And then you can use a liquid source. And the advantage of using liquids is that if you have, say, a big silicon wafer that's all intrinsic and you want some areas doped and some not, because you may want to dope some of it one way and some of it another way. So you can actually, if you use liquid, you can kind of mask off part of it and not expose it to that. So that's kind of a good way to use. But all of those things kind of are used depending on what one wants to do. Diffusion is good for several reasons, and it's bad for several reasons. So one reason it's good is you can take a bunch of wafers and just process them all at once. So it's efficient, not expensive, and efficient. However, diffusion happens not just in one direction, but in three, because it's a three-dimensional object. So sometimes the dopants can go places you don't want them to go, and that's not good. That's not something we want. Also, what happens when you use diffusion is everything has to be heated at the end in order to reconstruct the lattice and make all the dopants part of the lattice. Remember, I said it was kind of messy when everything diffuses in and it all goes in different places. And the heating goes up to like 1200 degrees Celsius, so really, really, really hot. That kind of makes the final extrinsic material possible. So the heating at the end is necessary, but that can actually cause issues depending on what you want. You can have dopants that you wanted to keep and they diffuse out because you have a high temperature. So advantages and disadvantages. The other way that is done is known as ion implantation. And that's basically where you take ions and just shoot them through an electric field and just hammer at the wafer with these stream of ions. It can be very, very, very precise. The machines that shoot these dopants at the semiconductor material can be set to penetrate to a certain depth, and that's it. And it can be very, very, very accurate, which is good. You don't have to cover, if you want regions that are not doped, it doesn't have to be covered with like something major, just photoresist layer, and that's it. So it's easier in some ways than diffusion processes, which actually have to be masked a little better. So that's good. However, one of the things that happens, and this is sort of similar to diffusion, but not exactly the same, the dopants hit the wafer at like high velocity. And when they do, they break bonds, they break the structure, they hit atoms, they knock things out of the way. So again, they kind of create a mess a little bit. But this also gets heated, It gets heated to repair the damage, but it's not nearly as much heating as you would do with diffusion. So it's heated, but not to 1200 degrees C. It's much, much, much less than that. So it still needs to be heated at the end to repair the lattice structure, but not too much. So characteristics of this versus diffusion, very accurate, which can be good. As you can imagine, it's also more expensive because you have to have the equipment that will shoot the ions. You do it at room temperature and then just do heating at the end, which is somewhat minimal. So nothing diffuses. So diffusion actually doesn't take place, which can be good if you've got areas that already have dopants in them and you don't want them to go somewhere. That's good. The dopants don't go to places you don't want. You need high vacuum, so that adds to the expense of ion implantation. So those are the two methods of doping. I don't expect you to remember that much about them. You just need to know that they exist. Intrinsic silicon, we've seen pictures of it before. You've got a nice, stable lattice structure, and that's how intrinsic silicon works. If we dope silicon with, say, phosphorus, phosphorus has 5 valence electrons instead of 4. So what we get are these extra electrons. And you'll notice that they really aren't part of the structure. They're just outside of the structure, and they basically can just move. They can move all over the place. They're not particularly bound to any particular area. And one of the reasons for that is that donor atoms, and donor atoms are what we call atoms that have an extra electron because they're donating an electron. So donor atoms add electrons. The energy level of donor atoms is a lot higher than the energy level of the valence and conduction band levels. So what this means is that the energy donor, you'll notice it's just below the conduction band. And what that means is it just takes minimal energy to get those electrons to move to the conduction band because they're not particularly bound. And it leaves behind positively charged ions, but they're not going to affect how this works. So the energy level of donor atoms is higher than the energy level of electrons that are just in the regular structure, so they tend to move better. So you get ions left behind in the valence band, but not holes, because these are just giving an electron and not creating a hole. So this means that all the electrons that are brought in by the dopants are just electrons that are added, and no other holes are added, which means there will be more electrons than holes. So this is what we call N-type material. N-type material is any type of extrinsic semiconductor material that has more electrons than holes. If we were to dope silicon with something like boron, which has one less electron, it only has 3. When we do that, you'll notice that next to every boron atom, there's just a gap. And what ends up happening is adjacent electrons will drop into those spaces, and those will end up kind of moving. They move a little slower than the others, but you see they just kind of shift around and gradually will just kind of move from one place to another. And they basically, we call the holes moving. Even though they aren't really moving, we act as if the holes are moving, and those are positive charge carriers. And you can imagine if you actually add some kind of force to this, the holes would move in a particular direction. Right now they don't, because there's no particular force to do that. So we call these acceptor atoms. They're acceptor atoms because they're going to accept an electron from somewhere. And what they do is they accept electrons from the valence band and they leave behind holes. In accepting electrons, they become ions, but the holes are left behind in the valence band. And no new electrons are made, so now we have more holes than electrons. And we have p-type material, which are the only two types that we will have in here. But boy, you can do a lot with n-type and p-type material. So the last thing I'm going to cover is, it's more theoretical than anything. I've never asked students to actually do anything with this mathematically, but it's something that you should know. Anytime you have an electron and you need to move it to the conduction band, there's a certain amount of energy that's required to do that. So we can actually calculate how much energy is needed to actually get these electrons to move. And we can use the energy equation from the first part of the course. Remember that weird one that had the effective mass and the charge of an electron to the fourth and all that, and that was the total energy. And we need to modify it just a little bit because now we're not in free space, we're actually in a lattice, but that's not difficult to do. So what we're going to do is we're going to figure out how sort of the radius from the nucleus that the orbiting electron will be at. And it takes both the effective mass of the electron and the permittivity of the semiconductor material into place. So notice that on this particular equation, the permittivity right there, that's the permittivity of free space. We're not in free space, so we're going to change it just a little bit, and we're going to use the relative permittivity and figure out kind of what this orbiting radius is. Note that in the equation above, you have A naught, that was the Bohr radius. We talked about that earlier. That's just where we expect an electron to be. And the n is just the quantum number, and then the m naught over m star is not the effective mass of an electron. It's actually the conductivity effective mass, which is different than the actual effective mass. So this is a different value. And it's one that I don't think I've ever asked a student to actually use. So you can just watch and learn. So also notice that in the equation that m star over m naught is inverted. So I know what it is because I looked it up on a table. In Appendix B, in the back of the book, it has the conductivity effective mass of an electron. So, and then we know the relative permittivity of silicon. We've looked at that before. So we can figure out a donated electron for n equals 1 in silicon and figure out the radius that we would expect to find it from the nucleus. And remember, with most things at n equals 1, we expect to find it at the Bohr radius, about 5.43 angstroms, something like that. So if we go through and actually figure out what the radius that it's orbiting, at which it's orbiting, we can put numbers in here, and remember my m naught over m star is inverted here, so that's why we have 1 over 0.26. And when we calculate that, we get 23.9 angstroms. The lattice constant, remember, is about 5. What this means is that donated electrons are like going around tons of silicon atoms all at the same time, not just one. The electrons that are associated with the silicon atoms, they're going right within the close confines of the silicon atom. The donating atoms, they're way out there. And that's why it doesn't take much energy to take them away from the nucleus, because they're already orbiting a whole bunch of silicon atoms. Even though the nucleus is part of the structure, the electrons are a lot farther away. So what this means, we can figure out the ionization energy. The ionization energy is just how much energy it takes to get from the valence band and in the structure into the conduction band. And we can do that using that electron equation that we did earlier. And we're going to use the relative permittivity as well as permittivity of free space and put in a whole ton of numbers. I can even say a butt ton because that's an actual thing. It's not actually a bad thing. It's just a thing. It's a measurement, and it's big. And I can't remember what it came from, but it had something to do with big kegs of drink or something like a butt ton. I don't remember. Or maybe it's wheelbarrow loads. I don't remember. But anyway, there's a lot. And this is the amount of energy it would take, which doesn't mean anything to you because it's just in joules. So if we change it to electron volts, it'll at least give you some perspective. So if we divide by the charge of an electron, we get minus 25.8 milli-electron volts. Remember, when the energy comes out negative, it is bound to something. But it is just shy of zero. I mean, it is just below that. It is not much at all. The energy from the valence band to the conduction band in silicon is 1.12 electron volts. This value of energy is like 0.025 or 0.026 electron volts, which means that it's hardly anything. It'll just go. So that's why donor electrons go into the conduction band easier, because it's just such a small amount of energy that's actually needed. So I'm not going to expect you to remember all these different donors and acceptors, but I do want to point them out. They all have relatively similar ionization energies, that they're all much less than the band gap energy. And you'll notice that for silicon and germanium, you can kind of have similar donors and acceptors. We can have phosphorus and arsenic as donors and boron and aluminum as acceptors. And you'll notice in germanium, the ionization energy is less. And in germanium, the band gap energy is also less. It's like 0.66 electron volts, so it's about half what it is in silicon. The interesting thing, though, is if you get to gallium arsenide. Gallium arsenide can actually use silicon and germanium as dopants. You're making gallium arsenide out of a group 3 and a group 5 compound, and they're put together, and they're equal amounts of gallium and arsenic put together. And I can't remember the band gap, but it's pretty big for gallium arsenide. I can't remember what it is exactly, but it's larger than silicon. So you notice that the ionization energies are a little bit bigger, but still, much less than the band gap energy. The interesting thing about gallium arsenide is that dopants actually kind of replace the group 3s, and then the group 6 dopants replace the arsenic, so there's actually a bit of a different mechanism. It's not all equal. So in silicon or germanium, whatever you add just replaces silicon or germanium. But when you are actually putting in a donor impurity which has an extra electron, that replaces the arsenic. If you put acceptors in which has a less electron, that actually replaces the gallium. So it's a little bit different. Interestingly, like I said, silicon and germanium can be dopants for gallium arsenide. And depending on what they do, that will depend on whether they're donors or acceptors. So if you add silicon and germanium, if they replace gallium, they're donors. If they replace arsenic, they're acceptors. So they can be either one in this particular compound. So that basically is just giving you a overall idea of how impurities are added.